Hi, I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. And this video is introducing the Magnetic Resonance Research Center at Arizona State University, which is in Interdisciplinary Science and Technology Building Number 1 on the Tempe campus. This is where all of our magnetic resonance instrumentation is housed for the university. What the primary thing we are able to do is nuclear magnetic resonance and magnetic resonance imaging. And the first thing we concern ourselves with is safety in the lab. And it has a unique aspect to safety because of the high magnetic fields. And so besides standard lab safety practices, we have some very specific safety that has to do with strong magnetic fields, because these magnetic fields are always on. So we're using large superconducting magnets where the superconducting field is always generating magnetic fields. It's never turned off. And so we have specific safety boundaries around each magnet which define where you start generating high magnetic fields. And this can be a problem for if you have certain metals that are magnetic, magnetic strips on credit cards, also phones, other things, pacemakers, and other types of metallic systems where you have magnetic components associated with them. Also, these superconducting magnets are cryogenically cooled. And so the safety around very low temperature cryogens is also of concern, especially when we're filling these magnets. And this is showing some of the outgassing of, for example, liquid nitrogen. And then lastly, we're often in nuclear magnetic resonance. We're typically putting thin-walled glass tubes where we fill them with solvents, things like chloroform or different acetone, different solvents where you have to worry about the toxicity and the safety hazards around the chemicals you're putting in the NMR tube and the solvents you're using, et cetera, for running this. Now, in the Magnetic Resonance Research Center, we have numerous superconducting magnet systems, including two high field systems, an 800 megahertz and an 850 megahertz magnet system. And we basically have fields ranging from 9 Tesla all the way up to 20 Tesla. And these NMR systems, nuclear magnetic resonance systems, can do liquid samples, which are most commonly run, solids, and a couple of our NMR systems have micro MRI or magnetic resonance imaging capabilities on them as well. And this is a picture showing from one side of the lab some of our different magnets, like our 850 megahertz system here. This is a 600 megahertz NMR. We have an 800 back here. We have some around the corner over here, etc. And one of the new additions in the Magnetic Resonance Research Center is a set of completely automated NMRs, specifically a new 500 megahertz Bruker system and a 400 megahertz, where you have sample jets or express auto samplers here. So you'll walk up to this area over here. You'll be able to enter the name of for a file that it will create, the type of experiments and the solvent that it's in, and your spentropy name, which is a cloud service where we store all the data. And then once you've entered that, it'll tell you a position, on this auto sampler to be able to put your sample into the magnet. And it will automatically run however many samples you submit to it, put that data directly on the cloud for you. And so we have a series of automated NMRs where you can either come into the facility and run them directly, or have samples shipped to the facility and run on this instrument your samples sent back to you and the data as soon as it's collected immediately stored on the cloud. And besides having all of these instruments for research purposes, for outside people to be able to come and do magnetic resonance, typically to look at molecular details or in the molecular sciences to be able to look at molecular details of a compound or of a matrix that you're interested in. But we also have several things to kind of illustrate educationally some of these instruments. So some of our old NMRs we've cut open so that you can start seeing, for example, the superconducting coil and where the liquid helium would go versus the liquid nitrogen, and some of these things, some probes, both solids probes that do magic angle spinning, as well as liquids probes, so that you can see kind of some of the internals and some of the basics of the hardware and instrumentation that goes behind doing magnetic resonance. Because at ASU, we have both undergraduate classes, graduate classes that use this, as well as these are heavily used for research purposes. And so what can we do with magnetic resonance, in the Magnetic Resonance Research Center at ASU? We do everything from what is typically molecular level structural characterization, which is probably the most common, where we can quantify different chemicals. We can look at distance and angle constraints to try to get molecular orientation of molecules, kinetics and equilibria properties, magnetic interactions in materials. You can measure diffusion and molecular dynamics directly in these things. And like I said, kind of micro MRI. So showing what I would say is a very common, two-dimensional homonuclear NMR type experiment where you can use these to walk through distance constraints and or bond constraints in a molecule to be able to get a molecular picture of the molecule, or to be able to get a real spatial picture, like, for example, here, the micro MRI, magnetic resonance imaging of black widow spiders, which I've shown here. And we can do reaction dynamics, micro MRI, et cetera. So these are all capabilities that we have available, and we do have automated for what I would say routine organic and organometallic molecular characterization. So hopefully this gives you a brief introduction to some of what we can do in the Magnetic Resonance Research Center at ASU. And please, at ASU at the website, you can look up Magnetic Resonance Research Center, contact us for anything you would like to run, both through educational online classes, on-ground classes, and research-related projects. Thank you.